Hello, AP Chemistry, and welcome to Chapter 15, Chemical Equilibrium, and we're going to cover sections 15.1 through 15.4. Now, note that 15, 16, and 17, which, like it says at the beginning of the chapter, all cover equilibrium just from kind of different aspects. So in chapter 15, we're going to introduce the general idea of equilibrium, what chemical equilibrium means, and the kind of math that equilibrium requires from us. And then we sort of like fill that out from the context of acids and bases in the next chapter. Okay. So this chapter really, really important because this sets the foundation for all the math that happens in the next one. Okay. So for starters, what is equilibrium, right? So from a macroscopic point of view, equilibrium is the place where there are no further visible changes. Okay? From a macroscopic point of view, it's the place where there are no further visible changes, right? From a microscopic point of view, right? This is what we're talking about. From a microscopic point of view, we could say that the concentrations of my reactant and my product no longer change, right? And we know that they change because here, right, we can see that we consume our reactant, we produce our product until eventually their concentrations no longer change, right? And that is because, right, going back to this figure and the stuff we talked about in the last chapter, the rate, right, the instantaneous rate is what? Right, the slope of the tangent at any point when we have a concentration versus time graph, right? Which means that if we think about the slope of my tangent line, the slope of my tangent line is decreasing, decreasing, decreasing until we hit a plateau, right? Likewise with my reactant, till we hit a plateau, right? Which is why, right, the amount of product and reactant stay constant because the rate of my forward process equals the rate of my reverse process, okay? So when we talk about equilibrium, macroscopically, no further change. Microscopically, concentrations are constant because the rate of the forward reaction equals the rate of the reverse reaction. Okay, now, note that equilibrium is established whether we start with reactants or we start with products or we start with a mixture that allows us to go in either direction, okay? So here, this is for the production of ammonia, right? So this is saying if we have some N2 plus H2 to make some NH3, right? So if we look at this, right, for this reaction, we can start with all of our, so this is my product, right? If we start with some nitrogen and we start with some hydrogen, eventually they react, they consume each other, they produce this until eventually we reach equilibrium, right? Likewise, if we just start with NH3 in the vessel, right, if NH3 just starts there, eventually that will also decompose to form some of my hydrogen and nitrogen, right? Which is why to date, and this is what I wrote at the beginning of your outline, right? Reactions going only forward, right? That's what we talk about as sophomores, right? Because otherwise we can't really do basic stoichiometry if we have to think about reactions going backwards, right? But it's true, right? A lot of processes are reversible, in that they can go both forward and backwards, right? We're going to start qualifying our processes, right? Which ones only go forward, which ones go reverse and forward. But that's the idea, right? Is that product particles can run into each other. Product particles can react just as well as reactant particles. Okay? So note that equilibrium is established whether we start with reactants or products or with an appropriate mixture of my components, right? So for example, if this was A plus B yields C plus D, right? If I had C and D in the vessel, they could make A and B. If I had a little bit of every piece, then we could have forward and backwards. But if I only had C, for example, there would be no forward and backwards because C requires D to make A and B. Yeah, does that make sense? Right? Same principle if I just have A in a container, right? It's not going to make any product because it needs B to be present with it. Yeah? Okay. All right, the equilibrium expression. So kind of like when we were in the kinetics chapter, we talked about how when you're asked to provide a rate law, that's a very specific thing that's asked of you, right? We want something that says rate is equal to K times whatever my concentration is raised to its respective order, right? That's what we want when we talk about rate law, right? When we want an equilibrium expression, we mean the same thing, right? Where our equilibrium expression, capital K, is equal to the concentration of my products, this time raised to their respective coefficients, okay? Not to be confused with rates. And truly, that is always on the multiple choice section, where there's something about equilibrium expressions versus rate laws, and whether or not coefficients come into play, right? Because people are going to confuse that. But you're not going to, because you are so attentive and such a delightful student, right? Right. Okay, so anyway, equilibrium expression, capital K equals my products raised to their coefficients over my reactants raised to their coefficients, okay? Now, your book does give you the derivation for this, right, which does come from the concept of our rate laws, right? Because if we think about, if we were to write the rate for the forward reaction, the rate for the forward reaction would include these two things, right? The rate for the reverse reaction would include these two things, right? Which is why this is also equal to Kf over Kr. Okay, and that this provides us information about my relative rate constants. Note that this does not give us our actual rate constant values, but it does give us the relationship between our rate constants. Okay, so when we're asked to provide an equilibrium expression, this is what we're asking for. Now, interpreting K. Now, if we think about this, right, at its essence, and this is what we talked about when we talked about chapters 5 and 19, at its essence, this is the relationship between product, right, and reactant. Okay, we have coefficients, etc. But essentially, right, the essence of it is product over reactant, which means that if we have a large K value, right, so a K value that is significantly greater than 1, what does that mean? Right, it means we produce a boatload of product, yes? It means that when we reach equilibrium, when we reach the place where macroscopically there is no further change, right, that means we have more product than reactant present, right? Which means that this would be an example of K significantly greater than 1, right? Now, if we have K significantly less than 1, what does that say? Right, it means that we have a significant amount of reactant relative to product when we reach our equilibrium state, right? Which this would be an example of, right? Wherein we convert very little of my reactant to product, right? And here, right, we would have something in the middle, right, where we have some reactant, some product, and so this would have a K value closer to 1 than the rest of these. Yeah, makes sense? Okay, now, once we have a K value, we can obviously manipulate our equation to manipulate our K, right? So for directionality, right, we just said reactions can go forward and backwards. If we're talking about Ks are always for the reaction as written, right? So if we talk about, for example, going back here, right, the K for this is based on this as written. If we wanted to flip our reaction, we would have to basically flip our K, yes? Okay, so if we wanted to flip our reaction, we could flip our K. If we wanted to scale our reaction, if we wanted to multiply our reaction by 2, thinking about what happens to my coefficients, right, that means I'm going to square my K, yeah? Because if I double all my coefficients, right, that means all those coefficients go up there as my exponents, right? Now, Hess's law applications. If I need to know the K value of a reaction and I have some equations that sum to that reaction, right, then it shows the derivation in your book, right, and you can actually work it out piece by piece, and you put the K values next to each other to cancel out what cancels. But the point is, the end result is that we're going to multiply our Ks, right? So if we add equations, we take the product of my Ks. Now, special case of heterogeneous equilibrium, wherein not everybody is in the same state. Okay, so here we see that this is a solid that forms two aqueous products, right? And not mentioned is that this is the dissolving, right? This goes back to that section where we talked about activities of pure substances, right? Aqueous means a solution, right? Solid, pure substance, okay? When we're talking about a pure substance being intermingled with a bunch of mixture stuff, right? It is going to always be excluded from our equilibrium expression, right? So our equilibrium expression here is going to be that's going to be our equilibrium expression because we're going to exclude this PbCl2 solid, right? Pure substances, either pure solids or pure liquids. Pure solids and liquids are excluded from our equilibrium expressions, right? Going back to the activities, right, their activities would just always be 1, going back to their reference value, right? But from a, I guess, more logical point of view, right, if I have a pure solid, PbCl2, right, its concentration cannot change, right? If I double the mass of this, I double its volume, etc., right? So the actual concentration of my PbCl2 can't change, which means that it can't be part of my K expression, right? But if we think about, for example, a beaker here, right, we have to have, in order to establish equilibrium, right, we have to have some solid present, right? Going back to what we talked about at the beginning, right? All of these species will be present at equilibrium, which means that even though it's not part of my expression, if I don't have some solid here, my scenario will never reach equilibrium, right? As point of reference, right, here is this equation, right, where we have pure solid, and a gas, which means that the K expression here is actually, right, KCO equals CO2, right? Which means that as long as I have some of both of these present, I will reach equilibrium, and that equilibrium will be represented by the same amount of CO2, right? Which is what this picture is hoping to convey, right? We can have a lot of the calcium carbonate and a little bit of calcium oxide, and we get this number of 1, 2, 3, 4, 8, 9 CO2 molecules, right? Likewise here, if we have a little bit of calcium carbonate and a lot of calcium oxide, right, we still get the same amount of CO2 because we've reached equilibrium, right? Yes? All right. Ponder that and think on it. And I don't know. I think that's all. All right. Be good. Have a great day, and I'll see you soon. Bye.